Having looked at our fundamental theorem of calculus idea and its relationship to the sketches of antiderivative graphs, we'll now work through a few more examples. In particular, we'll look at this S-bend curve here, and we'll remind ourselves about the relationship between these two graphs. If this is our little f of x, and we're attempting to generate the graph of its antiderivative, we can always work backwards and get the derivative graph. The derivative of this graph should be the graph we started with. That means that the y values on the graph we know translate to slopes on the graph we're trying to build, and also that integral or area values on the graph we know translate to changes in f values on the graph that we are trying to build. Okay. The other piece of information that we're given this time that we weren't before is an initial starting point. So f of 0 equals 2. Again, we could have any vertical shift in principle. Here we've been given a starting point to work from. So let's start at 0 as our reference point then, x equals 0. As we move to the right here, we have in this entire range, we have the y values are positive, and so the matching set down here is that the slopes are positive. Y values translate to slopes. And the slope is initially 0, in fact, so we have a 0 slope to begin with, and then it goes positive. On the first range from 0 to 2, we see 0 slopes gradually changing until we reach slope 4. So we'll roughly sketch this out. At that point, the slopes stay at 4. The y values in this graph stay at 4. The slopes on this graph stay at 4. So we actually have a straight line for this interval here from for x equals 2 to 4. Y equals 4. Slope equals 4. Now, what extra detail can we add? Well, we can look at the area underneath this graph, or its integral, and use that to determine how much change in f there is between, say, 0 and 2x value. Well, we can do that fairly easily because we have nice triangular and rectangular regions here. This area is 2 by 4, that's 8, and it's a triangle, so it's a half of that. That area is 4. And actually our sketch here did that pretty well already. So this change here over 0 to 2, so the area represented on the interval on this graph from 0 to 2 corresponds to a change in f on that same interval of 4. Area equals 4, change in f equals 4. On this side, the area of this rectangle is going to be 8, 2 by 4, and so we go 2, 4, 6, it would be up here at 8. The graph would continue on, and this change would be 8 units. And that completes actually our detailed analysis of the right-hand side here. We'll add our little axis values to make it to scale, but we're good to go. On the left, it takes a little bit of mental gymnastics to do this, I think, but it's fairly straightforward. Imagine coming in from -1 towards 0. That's how most people would think about it. Over that interval, we have negative y values, and so we'd have negative slopes. So on this range here, we have y negative. So on the graph of the antiderivative, that's going to involve negative slopes. Okay. In particular, we have a branch of slopes that are all -2, and then -2 branching lower. But we can actually work through a little more detail and get some grounding points, some anchor points here, by again using the area. The area here is -1, because that's really the integral value. It's below the axis, and it's a 1 by 2 triangle, so the area is 1. What that means about our sketch is, on that interval, we're going to start here and go down by 1 when we move from -1x to 0 equals x. So that gap there is a delta f of -1 from the left to the right. And after that, The slope remains at -2. So we're going to have a sketch like this. Notice it's a bit steeper on this side. Why? Because the y values are 4, the slopes are 4. That's steep. On this side, the y values are -2, the slopes are -2 on our f of x, big F of x graph. And so we get shallower slopes of -2 there. And so we could add some other grounding points if we liked. The integral of this region here would be 6, -6. So from here down to this point here would be a change in f of -6. From here to here. And so that would give us a y value here of 9, which fits in nicely with the way we sketched out the slopes as well. So we could trim a lot of this information off. It's put in here mainly for teaching purposes. The key thing again is always that y values translate to slopes and integrals translate to the changes in the value, the y values, in the antiderivative graph.